delay. So let's get started. So I guess first thing first, I just want to remind you guys I need your presentation preference for the packages that you like to present. So actually I just remember last year actually I asked all of you guys give 3 different packages, like with of course with your own priority, but I guess this time I'll just ask you to give me 2. So just give me 2 choices that I will try to get you into the first priority. I have a special formula here, as you can see, that I would kind of optimize the global utility somehow of all your choices. So try to just not to have the problem of 10 TensorFlows or something like that, basically. So okay, whatever you need to know for now, as I said, you just need to think of 2 packages, first priority, second priority. Give me the names by Thursday. I didn't set up that assignment in Canvas yet. I will set it up today, so you should be able to submit it later tonight if you want to. And it should be. And of course, the order will be, as I mentioned, will be based on popularity. So the popular package will be presented first, and then okay. So just a quick recap of last time. We talked about some basic thing for regression, classification, so on for the last 2 lectures, and we talked about which regression, for example, which regression also, and so on, and linear classifier and softmax classifier. So the main thing, as you can see, all this machine learning approach, and also as you can see for neural network also, is you typically just introduce a loss function and then try to minimize the loss function basically tune your parameters such that you minimize the loss function. So it's more or less an optimization problem. And and actually today, I want to just digress a little bit first. I like to talk a little bit about SVM. So this is the last machine learning technique that is really the state of the art before deep learning, or actually, as Hinton said, that it's basically just neural network with 1 layer or something like that. Or you may think of that way, maybe. So. But the idea is very simple. Support vector machine. Of course, SVM stand for. I don't have support vector machine here. Support vector machine, right? Oops. Oh, this is getting funny. Let me restart again. So this is a support vector machine, right? The really famous support vector machine. And the idea is actually very simple. So typically, your support vector machine, you do have some feature. They call this kernel trick to map into high dimension. But ignoring that, basically you are in some feature space. You're trying to separate kind of different classes in that feature space. For example, here, I have, let's say, 2 classes here, one class with this black dots, and the other class with this white dots, or white circles. Then if you want to classify these 2 guys, you want to try to introduce a line to separate them, right? Separate these 2 classes, right? So what the support vector machine, the idea is that of course you can put in many different kind of way to separate these 2 classes, but you want to pick the one such that the margin is as large as possible. What I mean by margin is that if you think of this red line separating these 2 classes, then you think of the closest data sample, from this black class, from this line here, would be this one, right? So the distance is more or less here. And for this white one, will be like more or less here. And if you think of a margin that is kind of like a margin of error, you can have error with that, will be like this big, right? Something like. And you call this sample points here the support vectors, and that's why we call it support vector machine. So then the idea is very simple. We're just trying to find all this separating line, or actually in high dimension will be separating plane, such that this margin is as big as possible. And then so to do that, as you can see here, for example, if I have this determine this separation, this line is going to separate these two guys here. And let me check, let's say okay, if you go back to some high school, or I don't know, undergrad geometry, I don't know whether you have geometry or something like that, then this line, the function for this line will be something like w dot x equal to something, right? Let's say for simplicity, or like in this case, let's say just equal to b, and then I can move this b to other side. I have x wx minus b is equal to 0. And be really careful that this is a dot product here. So w is a vector, x is a vector as well, right? So then if you move along this, perpendicular to this plane here, so you should have wx minus b is also another constant, right? So here, I just assume that I adjust w and b in such a way that at the support vector, I will have w, and the plane hitting this support vector will be wx minus b equal to 1. It's okay with that, right? If it was originally equal to a, then I'll just divide b and w by a, right? So I can, without loss of generality, I can assume this one is just equal to 1, right? And also, on the other side, if my boundary here is exactly in the middle between the two support vectors, then the other side will be just minus 1, right? So I have 1 and minus 1 there, right? So now the question is I will claim that the distance between these two guys is actually 2 over w, and this w is the norm of w here. So it's not hard to prove, because if you think of that, let's say I have a vector here. Let's say I have this point here. Let's say this support vector is x1, right? Have some origin, whatever, something like x1. And let's say this is actually I have origin here. I just said this is x1, right? And this is x minus 1, right? So then I will have, let me draw nicely. I have this distance will be simply x1 dot w, right? Or actually x1 dot w hat, where w hat is the normalized w. Basically, I have shown here, right? So this is basically, again, it's just equal to x1 dot w hat, right? And then this distance here will be x minus 1 dot w hat. So therefore the distance will be just w hat dot x1 minus x minus 1, right? And but x w dot w hat is equal to w over the norm of w, and w times x1 is on this plane, right? So therefore w times x1 is equal to 1 minus b, and this other guy is equal to w times x minus 1 is equal to minus 1 minus b. So therefore, if these two guys, the difference between these two guys will be just equal to 2. So therefore W times x1 minus x minus 1 is equal to 2. So therefore like W hat dot this guy is equal to 2 over log of W. So that's actually the main things. So if you understand that, then basically we are just trying to minimize these guys, right? Because maximize these guys, right? Because this is exactly the margin. We want to make this 2 over the log of W as big as possible. Of course, with the constraint of these two equations here, right? That's how we need to make sure that the support vectors will satisfy these two equations here. So therefore, like the setup will be like this, right? So we want to maximize this, and also we want to make sure that basically for all the points in one of the class, let's say the class in this is called class 1, let's say, this will be bigger than equal to 1, right? Because on this side, right, bigger than equal to 1. And yi here, for that one here, y1 for simplicity, we'll just say the class label on this side is 1, and class label for this side is minus 1, so I can just absorb this class label also in here. Right, so then reflect. So therefore, like this, what I mean is apparently for I equal to 1 is basically saying I need to have, let me say, this is basically saying if I equal to 1, I should have W dot x1 minus b is bigger than equal to 1. Or this notation is a little bit awkward, honestly. Yeah, actually, this is kind of bad. I should change it. I should write. I should just write x here. X in something like class 1. Oh, wait a sec. Okay, actually, it's correct. Sorry, I got myself confused. So it's totally fine. What I mean is if xi is belong to this class 1, then I should have W times x1 minus b is bigger than equal to 1. And if xi is in class minus 1, then I should have W x1 xi minus b is less than equal to 1, less than equal to minus 1. Yeah. Right. So that this equation is just summarize both equations here. So it's just that. Yeah, because if xi is in class minus 1, then yi will be equal to minus 1. So therefore I will have that. If xi is in class 1, then yi is equal to 1. So I just have this. So. And then of course equivalently maximize this guy is equal to just minimize the norm itself, right? So and that will be basically the SVM optimization problem. And this is for kind of hard decision. I would say like you don't allow to break any rule, right? So you don't allow have any samples to fall into this inside this margin. But I can also have a soft margin SVM, so to loosen the constraint a little bit. So if I have a soft margin, I can introduce something called a hinge loss. It's like a hinge, it's something like that. So a function like this. So basically, if the value is less than 0, then it's equal to 0. It's like you typically use to combine with some loss. So if I have the value that I'm interested is less than is negative, then I will just say no loss. If it's positive, then it's just exactly equal to that value. That's the loss. And so with the hinge loss, then I can, instead of trying to put a hard constraint here, I would say I'll just try to minimize this guy, right? This the hinge loss function, this one here. So in the sense, if this is negative, then I don't care, right? It's okay. It's really good. So if this is negative, that means that this is satisfied, right? I just want to, is that really so? Because last year I made a mistake here. And no one discovered that, of course. Let's see. You guys are sure I'm correct, right? So if on the other hand, if it is violated, that means that like this is like less than 0 somehow, then the cost will be just equal to, so this guy will be minus, let's say minus 1, right? Then let's say it's some minus, right? Let's say minus 2. If this is less than 0, then the loss function will be just equal to 2, the loss value. Because this is just opposite of this, right? This will be just 2 here. The hinge loss of 2 is just 2, so I will have a loss function of 2, loss value of 2. So I will sum over all the samples, right? So that's it. This is the, so therefore the soft margin SVM will be just have expression like that. Any questions? And of course, this is only 2 classes. We can go to multiple classes. Let's say if we have multiple classes, then a simple generalization will be, let's say I have score is basically for each class L will be, I have some particular weight WL, and then my score is just a linear of that. So I basically will have like in some high dimension, let's say I have different classes. This is, let's say, W1, W2, and W3. That's basically pointing different directions. And I will have whatever, like which one gives me the highest value, I would say is belong to that class. So then, again, I hope to have my correct estimation will be like the high score is the class that I want. So then I can define again a loss function, something like, let's say the actual class is class L, that's the ground truth. Then therefore I want that score for L is bigger than any other score. So therefore like this would be larger than this, right? And I want to add a delta, just some kind of like a buffer there or like a margin there. So I'm not just bigger than Sj, but I'm kind of bigger than Sj plus delta, right? Am I right? Now I suspect this should be negative, honestly. Is that? Yeah, it looks like it should be negative. Maybe it's another. So each year I find a new mistake of last year. Everyone agree with that? Like, does it make sense? So what I want is like SL is not just bigger than Sj. I want to be bigger than Sj plus delta for all other classes. Wait a sec, actually. Yeah, I'm sorry, I totally confused myself. But you get what I mean, right? The problem, this is actually correct, but actually J is the true label. I need to be. I always have trouble like this, but the point is like as long as you get the main idea here, you can figure out the sign and all these things. So the main idea is like when this H is negative, then there's no loss, right? So I want this thing to be negative. So therefore I want Sj to be bigger than SL plus delta. So therefore it's correct. So that's fine. Yeah. So for all the other classes. So and therefore like we can for multi-classes will be just like that. So we want to maximize the margin or minimize this W here, with the constraint with the sum of all these hinge losses here, and so that's my quick introduction on SVM. I guess it's an important topic that I just want to cover quickly. Even though it's not exactly part of neural network, but it's really the last state of the art before like neural networks, or like before deep learning. Yes.
Perceptrons?
No. I mean SVM.
Oh.
Yeah. So perceptron. Now we go to. I didn't change the session here. This shouldn't be done to SVM. So now really go to some neural network stuff. So a little bit go back to the old neural network, like the oldest models, we call it the perceptron. It's more or less the same as like the current model. The only thing is like the classic perceptron, when it was introduced, the activation function, like you basically, again, you're going to weighted sum your inputs, right? And then you go for some activation function. And then the activation at that time was just a step function. But so therefore, like people also call, like when you have multi-layer, something like that, we call multi-layer perceptron. Sometimes we even call it multi-layer network or multi-layer perceptron. But it's not exactly correct, because nowadays when you have like neural network, you always never use step function as your activation function because it's not trainable. So and of course also because they use step function at the beginning, there's no way to train it, but it was still used somehow. Actually, according to Hinton, like he even mentioned like some of these systems still using that in his class, in his kind of 2012 Coursera class. But yeah, other than like it was stated by Hinton, honestly, I cannot find any reference about that. So, but in any case, I'm not sure like is perceptron any use anymore. It's probably convenient, or like when you typically what they did is like they only try one layer perceptron. They really, you have multi-layer perceptron, you don't know how to train it. One layer, they kind of train it by brute force, like you adjust that a little bit, adjust the other parameters a little bit, and so on and so forth. Not brute force, but some kind of heuristic. And and of course you can argue that like if you do something like that, it probably is better like just use SVM. So therefore, I really doubt there's any actual significance of using perceptron nowadays. But just historically interesting, I guess. So let me quickly move forward, therefore. Yes, one thing I guess I like to mention, like that's also the past era when they have using like perceptron and also SVM. As we also mentioned, like typically they have all the hand code features. So you have create your own features, and then you after you engineer the features, you have the input, like get your features, then you do the classifier using perceptron. So of course the attractive characteristics of deep learning is that you presumably you can train end-to-end, and then you can just generate a feature. I mean, the feature, what's that called? Yeah, you can do the feature training kind of automatically rather than you are trying to hand code your feature. Hand engineer your feature generation steps. So here I borrow slides from the Stanford Card CS231N. So this is just some naming convention for neural network. So you have like one hidden layers that typically called two-layer neural networks. So if you have two hidden layers, you have like three-layer neural networks. And all these, of course, all these new ones, in this case, is just a vanilla neural networks that it's just a weighted sum of this thing and then go through some activation function. So each of these new ones is weighted sum plus activation function. So the weighted sum, the weights we are not written here, of course, but always remember the weights here and is trainable. Typically, it's the weights you are trying to train it, but the activation function is kind of fixed. So, and of course, I have those ideas because we kind of borrow that from biological neural ones. And this is just a simple illustration for that. We have this dendrite, and I think it's going to what?
In regards to the activation function, it's just like related to the context of the training data.
Actually, nowadays many people will just fix the activation functions. They will pick several well-studied choices, and then they start from there. And if it doesn't work that well, but typically, like you use RELU, and many people just use that. Like they have a couple variations. I'll go more detail into those, but yeah, that I guess like the era of introducing new activation function as a research area maybe already passed. Several years, maybe 3-4 years earlier, you can consider as a research area. I'm not sure still like people study that much. Yeah, I guess all the possible combinations people think of already. Like, if you come up with something like really interesting, then maybe you can write a paper on that. But I guess it's kind of difficult after so many years. So if we come back to this guy here, so maybe you guys are better than me, like because you probably study biology, say, not that many years. My last time I studied biology is 20. I don't know how many years now. I need to really count. Wow, 27 or 28 years. I don't know. I don't quite remember. So, but I guess this fourth model here is on one of the new ones, then there's chemicals from the previous new ones, and I think it's a dendrite. You kind of like combine them together, and supposedly if there's enough kind of they have inhibitor, and the other way was the opposite of inhibitor. Stimuli or something like, if that is above the sum of, above a certain threshold, then we'll transmit the signal like through the axon and then to the other end. And the signal is kind of like, one way to model it is like with this weight code, because the strength of your signal is you cannot modify that. Or I shouldn't say whether it cannot modify or not, but it just happened that like from our nerve, like when they send a signal, it's basically the same voltage more or less. So, but if the neuron is more activated, then it will just, if trying to send a stronger signal, it will just basically send a higher weight. So it just should blah, 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 blah. So therefore, like actually this is one of the model. Therefore, like people call this a weight code model, but I would like to say like this is not the only model, and also like it may not be accurate or like adequate to really capture all the physiology of our brain and so on. So therefore, like I actually we won't go too much into this. This is probably a very interesting thing, but the analogy is more or less stop here. And what we have like is just like this very simple model. Most of the time, it's just weighted sum, have an iteration, and pass to the other side. So if we think of what we have last time, then we basically, or like we even earlier, we always have some kind of loss function, right? And we try to tune the parameters. In this case, these parameters will be all the weights in the real ones, right? Basically, all the weights here, right? And or like all the weights hidden in all of these real ones here. We want to modify that. And and then after you're going, let's say forward, you have some training data here, and then you have some observation at the end. Let's say from this observation, you want to compare with the ground truth, and then if close to this ground truth, then the loss will be small, right? So you can define the loss comparing this. Then we want to go back, right? We define the loss function. We want to go back and say, how do we change each of these coefficients or each of these parameters here such that our loss will be as small as possible, right? So, of course, we can, as I said, this is an optimization problem, and it's a very difficult optimization problem, but the easiest way out will be simply trying to do a gradient descent, right? Let's say if for some parameters here, if I can, let's say there's some parameters like P1, P2, or whatever, like I just call it PI, let's say. I want to see like how should I change this PI. So I should just say, want to look at what's the final loss, the partial derivative of the final loss with respect to PI, right? So if this is positive, by the way, if this is positive, what should I do? Should I increase or decrease PI?
I'm going to take a guess and say increase.
Do we want to increase the loss or decrease the loss?
Decrease the loss.
Yes. So now now if we increase PI, will the loss increase or decrease?
It will probably increase the loss if you increase the PI, correct?
Yes. So I guess you want the opposite, right? So yes, you if let's say if this guy is positive, then you will just want to reduce PI, right? So if negative, you will want to increase PI or something. So and of course, in general, you have the whole parameters. You can think of a big, huge vector, right? And let's say you have let's say even not say the parameters of all the nodes here, just parameters in this new one here. Maybe it's a vector P here. So therefore, I can find the gradient of this L with respect to this P here. So then how I should change this P would be something like P minus the gradient of P times some epsilon, right? Where epsilon is some scalar. So I want to go for some opposite direction, right? So let's say this is the real P, this is the original P. So along the gradient, if I go along the gradient direction, then I will increase my loss, right? So therefore, I want to go into opposite direction, so I will decrease my loss somehow. But in any case, as you can see, I need to find this gradient, right? All that you can think of, find this gradient is essentially meaning that I need to find the partial derivative of each of the element in this gradient here, or like this each of this pi here. So, and it's actually for all the new ones in the network. And if you find that, then the procedure is pretty simple, right? You do a stable descent, or you have like modification of like different variety of stable descent, but the basic idea are all the same. So then how do we find this gradient? The idea is like, as you remember, like we painfully went through some derivative last time.
Numerically now, that's how we find the gradient?
You can do that, but it's not preferable. Last time we numerically, we showed that numerically do that, but we also showed like analytically do that, but like it's a little bit painful here and there. But I also mentioned that you can go for like step by step as chain rule, right? So, and actually, yeah, the way to do that is like, it turns out to be pretty simple. If you think of like calculus and chain rule, you can think of ultimately you have some kind of parameters that you want to change, and then these parameters can be one of these. You can think of this as parameters is one of the input, and combine with like some other inputs, and do some processing, and do have something combined together, have something, and then this is some kind of operation. Let's say maybe it's some just summation or like some activation function, and then the output will go for another processing step, and then another processing step, and so on and so forth. Eventually, you have the loss function here. This the L value here. And we call this a computational graph. So we can find back the gradient just using chain rule along this computational graph, and basically propagate your gradient one step at a time. So therefore, like, it's known as the backpropagation algorithm. We'll go more detail into that, but just a high-level understanding of that. And remember, this is basically just chain rule, nothing really particular. It's so amazing you think of that. This is only chain rule, and it has been reinvented and reinvented many times. Like maybe probably by some mathematicians like in the 18th century. I'm not sure, but the earliest one people credit to some control guys in maybe 50s or 60s, and then in the 70s like machine learning guys starting to do something, and then like 80s I have more people like rediscover that, and all this like big name actually kind of reinvented this like a couple of times. But if you really look at that, it's extremely simple. But I would say just because I do stuff, typically if it's the right thing, it will just either it will already be really famous, or it will just be reinvented, and it will just reappear many times. For example, expectation maximization is another thing. Like people have different names for that, and so this backpropagation also like many kind of areas we introduce. So let's see. So as I mentioned, it's just chain rule, right? So you essentially just chain rule, but I guess it's much easier to explain it with an example, like as I mentioned, some computational graph. Let's say really simple example. Let's say I have like x, y, and z. I have a function here. You can think of this as actually the loss somehow. I don't know. Maybe like one of these value is your parameters. You want to find the gradient with respect to this guy here. So you have like step by step, right? You can think of like this is composed of like first have an operation like x plus y. I get this guy, and then this guy combined with this guy, multiplied with this guy here. So now what we are going to do is like, let's say we have some inputs like here, right? So by the way, we always say we find the gradient of your loss function with respect to some parameters here, or like we want to find the partial derivative of your loss function with respect to some parameters I. We don't interested in the well, it would be nice we know the entire function, but we don't necessarily need to know the exact analytical function. Of course, this can be like some kind of like function sign or whatever, but what we're interested in only what's the value for the current point, right? For the current P, what is the value? This is right. We are interested in, let's say, Pi is equal to some value like 0.234, let's say. That's the current Pi. So, therefore, as I said, like here, I'm actually interested in, let's say, this is the input, let's say this is the parameter. I'm interested in what's this parcel F, parcel Y, when it's equal to 5, let's say. And also, or not just Y equal to 5, but also like for the other guys is equal to X equal to -2 and C equal to -4 and Y equal to 5, let's say. Then the way to do that is first we go forward. So we go forward, it's like we have the input is here, then we just go step by step to compute the values, right? So I have X plus Y, so I have this 3 here, and this multiplied this, I have -12 here. And when we go forward, at the same time, actually, we also should compute the partial derivative of all the outputs with respect to each of the input. That will be useful afterward. For example, like the partial derivative of this output with respect to X, what is that? What's that?
Partial derivative of what?
The output with respect to each of the input. Let's say with the first input, the upper input. What is that?
1.
Yes, 1. 1. Because this is, I just give a name here. What was give a name? Let's call this, maybe I will have a name here. Oh, okay. It was Q, called Q afterward. Let's say this is Q. Then Q is equal to X plus Y, right? And I have partial Q, partial X is just equal to 1, right? It doesn't have anything to do with the input. This is independent of the input X and Y. Mm-hmm. So, also like for this partial derivative Y, Q with Y is 1 also. So, and then when you have, you will store it. Actually, in practice, you will store it somewhere when you compute it. And you have the output here now. The output is the input of this guy, right? Then again, you compute this output, but also you compute the partial derivative of this output with respect to all the inputs. So, so therefore, partial derivative of this with respect to this is what? First, I mean the upper input. Partial derivative of F with respect to Q. Yeah? What?
Z.
Yes. Z in this case is equal to -4, right? So, I mean, F is equal to Q times Z or Q times Z. Then partial F, partial Q will be equal to Z. And then therefore, like, it's just equal to -4 in this case. Again, like in this case, you store -4 here, store 3 here for this guy here. That's basically partial Q, partial Z. So now if I want to go backward to find basically the partial derivative of F with respect to all these X, Y, and Z. So let's just trace back. So if I trace back here, partial derivative of F given Z is already given, right? Here, we already computed that. It's already here. So, partial derivative of F given Q is stored here, right? It's -4. And then okay, right? We have -4, right? So partial F, partial Q is -4. Now, partial F, partial X will be equal to partial F, partial Q, partial Q, partial Q, partial X, right? And partial F, partial Q, we just got it. We propagated like earlier from the earlier RELU one. And now parcel Q, parcel X, we computed that during the forward pass. It's just equal to 1, right? We stored it at this little one. So therefore, we just have this multiplied by this guy. I get -4 here, right? And then down here, parcel F, parcel Y. Let me write a little bit. Parcel F, parcel Y is 0. Parcel F, parcel Q that we got earlier is -4. And times parcel Q, parcel Y that we computed earlier equal to 1. So it's equal to -4 again. So you see, it's really very simple, honestly, right? Once you write down the computational graph, what we do is basically during forward pass, you compute the value of the output, but at the same time compute the value of the partial derivative of the output with respect to all the inputs. And then when you going backward, you just like multiply the derivative that you propagate back with whatever you store the partial derivative in each of the little one. So therefore, it's just called backpropagation in this way. You forward once and then backward once. You compute all the partial derivative with respect to all the inputs, and also all the intermediate inputs as well. So this is just repeating what I said. And that's basically that's also repeat what we said also, like during the forward pass, we not only compute the output, we also compute the partial derivative of the output with respect to like each of the individual input. And then when we go backward, you receive some partial derivative from the later layers. And then you multiply this gradient, this partial derivative with each of these things we already store and then propagate back. So I think it's pretty clear. This is another example. It's more or less the same. So the only thing I like to emphasize here is that like if you what we can do, of course, I have a function like this. Let's say I can build a computational graph and split the whole thing. Say I have this W0 to X0 and W1 X1. So I mean this final thing F Wx, as you can see, is first construct this W0 X0, then I have W1 X1, then I add this together with this W2, and then I need to multiply -1 and do exponential +1, and then take take a inverse for that one. And of course, you can do exactly the same thing like for both forward backward. One thing as I want to emphasize here is like I can build computational graph in many ways, right? For example, like I can combine some of these functions here, right? For example, instead of I have a function like split in this way, you may realize that this actually is just a sigmoid function. So we can replace it also by one sigmoid function. Then in that case, you can jump through several steps here. But of course, you better have like these tiny components that you know how to compute the derivative. And as long as you know for each of these building block function, you know how to compute the partial derivative for the output with respect to the input, then you are good. And in practice, actually, that's what have been done like in maybe Fiano and PyTorch, right? They have all this like automatic derivative. So you give the function, they all know like how to. I mean, what was the supposing it was the derivative of the partial derivative of the output with respect to input. I don't know how they do that. Maybe they have a table for that. But in any case, yeah, we don't have too many different functions, right? I mean, of course we have special function, but still like I'm sure it's not more than like 1,000 different functions. I mean that we commonly use, or maybe not more than 100. So this just give another example, just to check your understanding. Let's say, I don't know whether this if I have, let's say this thing here, I don't know, they have kind of like the solution here, but in any case, I have this, let's say I have this mass operator. What do you think the partial derivative going back supposed to be? You know the mass operator, right? I have two values, let's say two input values here, I will take the mass here as the output. Now if I want to pass back the partial derivative for this mass function, what's the partial derivative of that output with respect to the input? Next time I should prepare a slide better because the solution is up here. So you, yes? Actually, okay. The solution is not obviously here. It's kind of more like a hint. I guess it's not that bad, but but my question is I have a max function here. Let's say x, y, x equal to 3, y equal to 4, and then I have a mass operator. Z is equal to, of course, equal to 4, right? So now I have a partial derivative. As you know, like when I do backprop, I need to compute a partial derivative of the output with respect to all the inputs, right? So what is partial? This is C partial X and partial C partial Y.
For X, it might be 0, and for Y, it can be 1. I think for this case.
Yes. So you can think of that way. So you have these two values for this case. Since y is already the biggest one, z is just equal to y, right? So therefore, like your partial c partial y will be just equal to 1 because it's like c equal to y. It's something like have a function like c equal to y. Then for the other guys, because this one is actually not the biggest one in the sense this output will have nothing to do with this input, right? So as long as this guy is smaller than this, I don't care whether it's like 3 or 3.1 or 3.2 or 3.4 or whatever. So this has nothing to do with this. Therefore, like that partial derivative will be just equal to 0. So and there's another example like RELU. It's a very common function. Actually, depend on context. Like earlier here we call it RELU. I think earlier what we call that, like we call it hinge loss. So it really depend on context. So so for the RELU function, yeah, again, like if bigger than 0 it's just itself. If less than 0, then it's if input is less than 0, then it's just equal to 0. So again, like if we have a RELU function, I need to give example as an if like x is equal to 1, y equal to 1, of course, then what is partial y partial x? In this case,
One.
Yes. So how about x equal to -2?
Zero.
Yes. So actually, I guess a simple way to say actually, this partial derivative is we only have one input. It's just the slope, right? You see, like when it's less than 0, the slope is 0, so therefore it's 0. When it's bigger than 0, the slope is 1, so therefore it's 1. Yeah. or you can argue like what I argued earlier, when it's less than 0, actually, then you break the really break the, what do I say, the dependency there. Then it's really y does not depend on x somehow, so the derivative will be 0 as well. So one more example, I guess I just give you guys a little bit thinking as well. So let's say I have, this is something that sometimes uses in computer vision or image processing, that you do it for, usually you do it for segmentation. You have, for example, like you have 2 inputs here. Think of that like I have, I call this RELU, let's say, RELU operator. The input will be like 2 image masks, let's say. Let's say I have some image, and I have a ground truth segmentation is here. Like I want to segment this person out. That's value like that. So basically, on this person, like everywhere is 1, outside that is 0. Then let's say I have, this is a ground truth, then I have a classifier that figure out a similar segmentation but not exact. So again, like inside is 1 and then outside is 0, let's say. Then my RELU operator will basically count the number of pixels that are kind of intersection of both images, both masks. That's the AND operator that both masks consider as 1 over the union of the masks. So there will be, let's say, somehow like I have maybe this part is overlapped, and then I have a bigger part is the union of that is like this guy. Then I have the number of pixels here over the number of pixels here, so it's a RELU operator. So again, like for this guy, then you need to think again, okay, for this, what will be my partial derivative of the output with respect to, let's say, a input input value there. Actually, this is even trickier because I guess this, let's see. I didn't mean to, like, I guess I when I acted, I didn't think too carefully. Let's say if I want to, I have 2 of this mask, right? And let's say if I change one of the values here, so changing the values will be, say, one of the mask value from 1 to 0. So how would it change with respect to the output? So let's say if I have, this is x1 and x2, I have like the pixel ij of this guy, the mask like changed from like 1 to 0 or 0 to 1, then how that is going to, so okay, I think I shouldn't go to whatever, to digress too far away. Like I guess this at least we won't come across this that much. So you may, and even you do computer vision stuff, most likely eventually you will just call a function, or like they will do auto derivative for you guys. But I guess it's good to think a little bit about this when you sit down and like think about you need to actually when this change and then like it's not how it's supposed to change on the output. It helps you to debug when you really write down the code. Like you don't know what you need to have some insight. Like when you write down the whole code or like you modify other people's code. Typically, like you cannot just go step by step, like line by line, and say, yeah, this line I catch the error or something like that. Like this is basically impossible. For me, like historically, I never did manage to find error by reading codes and find, oh, this line has problem, so therefore we didn't get the correct result. It's always like we think of like what do we expect? So let's try this, and then the result is not as expected. Then it must be something weird. Then let's think about another test that will check something else. Then get some other hints and do this again and do this again. So therefore, like it's actually very helpful, like to think block by block and able to get into this tiny detail when necessary. So anyway, like for this thing, I won't elaborate anymore because I already write it down. Like if you just write the function and try to change this particular pixel, like from 0 to 1, and you think of like how this is supposed to change, then that would be several different cases, right? If this is going to change from it's going to be bigger, then you know that I will have a positive gradient. If it's not going to change the output, then I will have gradient is equal to 0 in that case, and so on and so forth. So I guess let's see what else I have here. I have some vector variables here. I guess I may be stopping here. This vector variable may take a little bit more time. Any questions, comments? And but again, I just want to re-emphasize. I guess the take-home message is you really. I really hope you understand the backprop. I should even say high level. I guess you can understand backprop very much in detail because it's such a simple algorithm, a simple procedure. You're just trying to, when you do forward, you're just trying to compute all the output and at the same time all the partial derivative of that unit, computation unit, of all the output with respect to the inputs. And then you do the backpropagation. You just propagate back the derivative and at the same time multiply back all the partial derivative that you computed earlier. So it's just that easy. And as I said, it's amazing that like people, yeah, and yeah, I mean, because you can take up papers, I guess you are able to, if you're interested, take up paper about backprop in the 70s, 80s, or maybe even when I took a class on neural network in the 90s, it's described in a much more complicated way. They look into a special case, particularly for this particular activation function, and then you're trying to compute a derivative somehow, and then you do some argument here and there. And it turns out if you look at it a different way, it's just so much easier. So I guess that's the end. So I'll talk to you guys on Thursday.